Organic Chemistry, Chem 213, Exam 5 Material, Part 2. Structure and bonding in amines. The bonding in nitrogen is similar to that in ammonia. The nitrogen is sp3 hybridized. The carbon-nitrogen-carbon bond angles are close to 109 degrees and tetrahedral. For the nitrogen atom, chirality is possible but not observed. An amine with 3 different substituents on nitrogen is chiral, in principle but not in practice, because the lone pair of electrons is considered a 4th substituent. Most amines that have 3 different substituents on nitrogen are not resolved because the molecules interconvert by pyramidal inversion. Here with our nitrogen, we see sp3 tetrahedral. We have 4 different groups on there. We have an arrow here showing us in the reverse direction and forward direction are just as likely. The pyramidal inversion, we have an sp2 hybridized planar molecule at this point. And what happens is it literally flips over and becomes the other compound. So what happens is in the pyramidal inversion, it actually flips back and forth between the R and the S. But it happens so rapidly that you cannot isolate them or resolve them. So we don't have either. So in possibility, there is the possibility on paper it could be chiral, but it's never observed due to pyramidal inversion. Sources of amine and their properties. Simple methylated amines come from the reaction of ammonia with CH3OH, that's methyl alcohol, in alumina catalyst. It also needs a temperature of 450 degrees. What this does is it yields a mixture of monomethylated, dimethylated, and trimethylated products, and these products can be easily separated by distillation. Amines form hydrogen bonding. Amines with fewer than 5 carbons are water-soluble. Primary and secondary amines form hydrogen bonds, increasing their boiling points. So on this graphic, we can see, remember, it's only primary and secondary amines that can do this. Tertiary amines do not undergo hydrogen bonding. Here we have nitrogen with its hydrogen. This hydrogen is hydrogen bonded to nitrogen on another molecule. And they're showing a series of bonding between different amine molecules. This is linear, but don't forget this is also happening three-dimensionally. There's some bonding happening in front of this and behind it also. So again, looking at primary and secondary amines hydrogen bond, and what this does is it gives them a higher boiling point than alkanes of similar molecular weight, but it does have a lower boiling point than alcohols of similar molecular weight. So what that statement is telling us is that the hydrogen bonding in an alcohol is stronger than the hydrogen bonding in an amine. My drawing on the left-hand side shows you 2 molecules of methylene showing the hydrogen bonding and the polarity. And what I'd like you to do on the space over here is to draw 2 molecules of diethylamine showing hydrogen bonding, and be sure to indicate the polarity on each atom. All right, I have my drawing here. It's a little rough, but you get the idea. What I wanted to show you is the template basically for any 2 molecules showing hydrogen bonding would be the nitrogen of one molecule being hydrogen bonded to the hydrogen on another nitrogen molecule. And depending on what they're asking for in the structure, do they want a diethylamine? In this case, they just had methylamine, so you only had 1 methyl group. In this case, you have 2 groups, so it's a secondary amine. These bonding lines here, what I would do here is I would go ahead and put my CH2, CH3, and my CH3, CH2, and over here CH2, CH3, oops, sorry about that, and my CH2, CH3. And there's obviously more than one way that you can do this, but you want to practice being able to show 2 molecules hydrogen bonding, and whatever molecule they specifically ask for, that's the structure you need to draw. You wouldn't be using R groups in this case. And looking at the last part, tertiary amines do not hydrogen bond, so they have lower boiling points than primary or secondary amines of similar molecular weight. Basicity of amines. The lone pair of electrons on nitrogens make amines basic and nucleophilic. They react with acid to form acid-base salts, and they react with electrophiles. Amines are stronger bases than alcohols, ethers, or water. Here we have our amine acting as a Lewis base. It's going to grab onto that hydrogen, forming a quaternary salt. Do you guys see it has a positive charge? And we have our anion there. So we have an amine reacting with an acid to form a quaternary ammonium salt. Relative basicity. Amines establish an equilibrium with water in which the amine becomes protonated and hydroxide is produced. The most convenient way to measure the basicity of an amine is to look at the acidity of the corresponding ammonium ion. A high pKa means you have a weaker acid and a stronger conjugate base. The Kb is given here when we have it acting as a base. The Ka is given here when it's acting as an acid. We tend to like to look at these numbers Ka and Kb in their logarithmic form. So we have Kb equals minus the log of Kb, and Ka is minus the log of the Ka. We can convert between the two. When we calculate one, we can look at the other by pKa plus pKb equals 14. The general pattern of basicity: most simple alkyl ammonium ions have pKa's of 10 to 11. Arylamines and heterocyclic aromatic amines are considerably less basic than alkylamines. The conjugate acid pKa is 5 or less. Table 24.1 in your textbook shows us the pKa of ammonia. And then as we see different substituents added to that, we can see the varying differences in the pKa of the different amines. Base strength. Alkylamines have similar basicities. Arylamines and heterocyclic amines are less basic than alkylamines. Amines are non-basic. They do not undergo a protonation when treated with aqueous acids, and they are poor nucleophiles. Amine basicity can be used as a means of separating amines. An amine can be converted to its salt, extracted from a solution with water, neutralized, and re-extracted with an organic solvent. Amines as acids. Some primary and secondary amines are very weak acids because the hydrogen can be removed with a very strong base. LDA is formed from diisopropylamine and acts as a strong base. It can be used further in reactions. And in fact, we've seen this reaction of making LDA before, and we've also seen LDA used in reactions when you see it written over an arrow. Basicity of substituted arylamines. Arylamines are less basic than alkylamines. Arylamine lone pair electrons are delocalized over the aromatic ring and are less available for bonding. Arylamines lose resonance stabilization when they are protonated. What we see in this graphic here is we have a lone pair of electrons on our nitrogen, and we have our benzene ring with it. And the arrows between each of these structures is a resonance arrow telling us that electrons are moving around. And we have 1, 2, 3, 4, 5 resonance structures. The more resonance structure, the more stable the molecule. When a molecule is stable, that means it doesn't want to change. So we can see by the way the resonance happens between there, we have an especially stable molecule here. Now adding something else to the ring. Electron donating substituents, such as CH3NH2 OCH3, increase the ring activity towards substitution and increases the arylamine basicity. Electron withdrawing substituents, such as chlorine NO2 C triple bond N, decrease the ring activity towards substitution and decreases the arylamine basicity. So on this slide, we are seeing a comparison of stronger and weaker bases. Synthesis of amines. Reductions of amides, nitriles, and nitro groups. An SN2 displacement with CN followed by a reduction turns a primary alkyl halide to an amine with one more carbon. That one more carbon came from right here, the C triple bond N. Our alkyl halide, so wherever the halogen is, that's your leaving group. That's where the attachment's going to happen. This carbon is going to attach wherever this halogen was. The next step of this reaction is the reduction, the lithium aluminum hydride in ether, and then we also have a second step in there with water. And now we have a primary amine, where this carbon right here came from our C triple bond N. We can also produce amine from a carboxylic acid. In this case, we're going to actually change it from a carboxylic acid. We're going to go ahead and put our nitrogen on here. Our NH2 group is going to replace where the OH is. And then we're going to have a reduction happening where the carbon of our carbonyl group is going to undergo a reduction, and then we have our primary amine. So this reaction is taking carboxylic acid and turning it into an amide for the reaction to happen. On our next slide, we're going to look at taking an amide and directly reacting it to form an amine. Amide reduction converts an amide or nitrile to an amine with the same number of carbons. It can form a primary, secondary, or tertiary amine. And the reaction that I have written here, all of these R groups can be hydrogen. So we start off with our amide. We undergo a reduction reaction with lithium ammonium hydride, ether, and then the second step water, and we saw that on the previous slide. And depending on how many R groups you have that aren't hydrogen, if these were both not hydrogen, we could have a tertiary amine. If this one was a hydrogen or this was a hydrogen, again, it could be primary, secondary, or tertiary amines are formed. Reduction of aryl nitro compounds. Aryl amines are prepared from the nitration of an aromatic compound and the reduction of the nitro group. This reaction is a catalytic hydrogenation over platinum. Now, this is only suitable if there's no other groups that can be reduced, such as alkenes or alkynes. This set of reagents is going to attack this nitrogen and convert it to an amine. Another set of reagents that will also reduce this NO2 is either iron, zinc, tin, or tin 2 chloride in an acidic solution. SN2 reactions of amines and alkyl halides. Ammonia and other amines are good nucleophiles. Ammonia, when it reacts with an alkyl halide in an SN2 condition, forms a quaternary ammonium salt. We can have a base come in and convert that to a primary amine. A primary amine can react with an alkyl halide, forming a quaternary ammonium salt. Under basic conditions, that can be converted to a secondary amine. A secondary amine can undergo the same reaction and form a tertiary amine. And a tertiary amine can undergo the same reaction and stop at the quaternary ammonium salts. So one of the limitations of this reaction is you have uncontrolled multiple alkylations. Primary, secondary, and tertiary amines all have similar reactivity. The initially formed monoalkylated substance undergoes a further reaction to yield a mixture of products. What we see here is the 1-bromooctane reacting with ammonia, and we get a monosubstituted, disubstituted, in about 45-43% here is what they're showing us, and trace amounts of tertiary and quaternary. Because we have the problem of multiple alkylations on the other reagents, we have a selective preparation of primary amines, the azide synthesis. The azide ion, it's 3 nitrogens with a minus charge, displaces a halide ion to form a primary or secondary alkyl halide to give an acyl azide. Acyl azides are not nucleophilic, but they are explosive. That's kind of interesting. The reduction gives the primary amine. So it seems like the advantage of this is we don't get multiple alkylations, but we have to be careful that we don't blow up our lab. All right, we have our halogen is our point at which the nitrogen is going to attach. We have NaN3, ethyl alcohol. The nitrogen is going to attach wherever the halogen was, and note that this nitrogen has 3 bonds, but the one in the middle has 4, so it has a plus charge. It has a formal charge of +1, and the terminal nitrogen only has 2 bonds, so it has a formal charge of -1. This then undergoes the reduction with our lithium aluminum hydride, ether, and water. We've seen that before. And now we have our nitrogen being, in this case, a primary amine. We can take aldehydes and ketones and have them undergo a reduction. Ammonia, primary amines, and secondary amines yield primary, secondary, and tertiary amines, respectively. All R groups can be hydrogen. Here's a ketone. Here's our nitrogen. In order for this reaction to happen, you cannot have a tertiary amine. This can either be ammonia, the smallest, or it could be a primary, secondary, because the key feature is this nitrogen must have an available hydrogen to get out of there. Tertiary amines will not undergo this reaction. So it can have more than one hydrogen, but it has to have at least one. This nitrogen is going to go ahead and bond to this carbonyl carbon, and through reduction, it's no longer going to be a carbonyl carbon. It's going to have an extra hydrogen on there, or a new hydrogen on there, and the oxygen is gone. So now we have formed an amine. Here's a poster from Compound Interest. Their website is www.compoundchem.com. And I was looking up information about amines, and I found this poster. Organic nitrogen compounds enter our atmosphere in a variety of sources, both natural and industrial. So I thought this one was interesting. It describes amines, amides, and some other compounds. So again, this slide is for your information to bring in chemistry into our everyday life. Two named reactions, Hofmann and Curtius rearrangements. Carboxylic acid derivatives can be converted to primary amines with the loss of one carbon atom by both the Hofmann rearrangement and the Curtius rearrangement. In the Hofmann rearrangement, we start off with an amide. In the Curtius rearrangement, we start off with an acyl azide. Hofmann rearrangement, what's going to happen is we're going to basically do a decarboxylation. That's loss of CO2. And what's going to happen is this carbon and this oxygen, and it's also going to grab an oxygen from this site here. This is going to be removed. Now the R group that was on this carbon here is going to rearrange and now be on this nitrogen, hence rearrangement. For the Curtius rearrangement, a similar thing's going to happen, but we do have a couple more nitrogens here. This also involves a decarboxylation. The carbonyl group here, with help of another oxygen over here, is going to become CO2. And this R group is going to rearrange and be attached to this nitrogen, and these two guys are going to go away from there. That's where the N2 came from. Both of these reactions involve a rearrangement and a decarboxylation. The Hofmann elimination converts amines to alkenes. The NH2 negative is a very poor leaving group. So it is converted to an alkyl ammonium ion, which is now a good leaving group. Here we have our amine, and in this case it happens to be a primary amine. CH3I in excess, and what happens is, because it says it's excess, this nitrogen grabs not only one of those, but it actually grabs three of those. In fact, it'll go all the way until it becomes a quaternary ammonium salt. We saw here that alkyl ammonium ions are a much better leaving group. And this is that iodine kind of hanging out here. I didn't really have room to write it over here, so I just happened to write it above here. Well, we can then take this alkyl ammonium ion and react it with silver oxide, water, and some heat. And then what we do is the carbon that had the nitrogen on it, the nitrogen's gone, and the carbon is now double bonded. It forms an alkene with the R group that it had next to it. And you can see this nitrogen with its three CH3 groups is now gone. This reaction, the less substituted double bond is formed because of the bulk of the leaving group. So you can see it says in this illustration that 94% here and 6% here. This basically goes against what we've learned before when double bonds were formed by elimination reactions. This is the opposite. The less substituted double bond is formed in the majority. Reactions of aryl amines. Amino substituents are strongly activating. They're ortho-para-directing groups in electrophilic aromatic substitutions. Polysubstitution sometimes occurs. We're starting off with aniline. Again, so this NH2 group, which is the amino group, is an ortho-para-director and strong activator. And we can see that what happens is we don't just get the ortho and the para, we actually get a combination of every site, ortho and para, being substituted. Arylamines are not useful for Friedel-Crafts reduction. The amino group forms a Lewis acid-base complex with the aluminum chloride catalyst, preventing further reaction. Therefore, we use the corresponding amide. So in this reaction, we have our amino group being converted to the amine first, and then the reaction takes place. After the reaction takes place, we can then reduce this amide back to its amine. Diazonium salts, the Sandmeyer reaction. Primary arylamines react with HNO2, which is nitrous acid. This is not nitric acid, it's nitrous acid. Yielding stable arene diazonium salts. Here's our amine group, HNO2, sulfuric acid, and we now have our arene diazonium salt. This arene diazonium salt can undergo a further reaction at this point with a nucleophile and then can be substituted. So what we see is the NH2 itself is not a good group to work with. We're going to have to change it to something else that makes the reaction better, and it happens at the site that we want it to happen at. The diazonium group of arene diazonium salts can be replaced by many types of nucleophiles in radical substitution reactions. On the next slide, we'll see some more examples of what this can be converted to with nucleophiles. We can substitute on our arene diazonium salt a hydrogen, halogen, chlorine, bromine, iodine. We can put our C triple bond N group on there, and that can be further reacted with to form another compound. Or we can use copper and convert that to an OH group. So we saw the nitrous acid before. Arylamines and nitrous acid. Arylamines react with nitrous acid, but the alkene diazonium products of these reactions lose the N2 rapidly, leaving carbocations. So we can see the nitrogen is attached here, but rapidly this nitrogen is going to get out of there, and here's where our carbocation is formed. Arene diazonium salts undergo a coupling reaction with activated aromatic rings, such as phenols and arylamines, to yield brightly colored azo compounds, and these can be used as dyes. So we have our arene diazonium salt. It's reacting with a benzene compound, and the Y group, the leaving group here, typically would be OH or some sort of a nitrogen group. And our azo compound is formed, and they tell us that this can be used as dye. So we now know that this compound is colorful. What makes an organic compound colorful, if you remember with our UV spectroscopy, is the alternating double bonds or the conjugated system. So take a look at this. You have conjugated system here, coming through the nitrogen and also coming through the other benzene over here. The electrophilic diazonium ion reacts with the electron-rich ring of the phenol or the arylamine. Usually occurs at the para position, but can go ortho if the para is blocked. Tetraalkyl ammonium salts as phase transfer catalysts. Tetraalkyl ammonium ions from their salts can replace inorganic cations to bring ions into the organic solutions catalytically. Cyclohexene in chloroform cannot react with sodium hydroxide and water because they're in different phases, but a small amount of benzyl triethyl ammonium chloride brings OH into the organic phase for the reaction. The phase transfer catalysis. The transfer of inorganic ions, this is OH, from one phase to another is called phase transfer, and the tetraalkyl ammonium salt is a phase transfer catalyst. We can see here that we have the aqueous phase and the organic phase, and it's only at the interface that anything can happen, much like that reaction of forming nylon. What we can do, though, is if we add the salt in here, the ammonium salt, we can now transfer the reactants between the two different phases. Inorganic nucleophiles can be transferred from an aqueous phase to an organic phase where they are much more reactive in substitution reactions. Spectroscopy of amines. The IR spectroscopy, the characteristic NH stretching absorbs at 3300 to 3500. That is the same area that we see carboxylic acids and OHs, so sometimes we will see that, sometimes it'll be masked, but it's in the same region. Amine absorption bands are sharper and less intense than hydroxyl bands. Protonated amine shows an ammonium band in the range from 2200 to 3000. So here we have a cyclo ring with nitrogen, and there's no other functional groups on there, so we can clearly see the NH2 at about 3300 here. I have more examples on the next slides. Here we have a quaternary ammonium salt, so we have our nitrogen group. This is a little less than the 3300. You can kind of see it in through here. And then we also have a very small one shown here, this nitrogen here. In fact, and if you didn't know that there's a nitrogen compound, you could have quite easily missed this. So again, with IR spectroscopy, once you know the compound, you need to go back and search out proof that it's there. Look for those kinds of peaks. Proton NMR. The hydrogens on the nitrogen appear as a broad signal without any coupling to the neighboring carbon. What that means is we're not going to have that coupling splitting of the signal, so we won't know how many it's next to. And the way that they prove this is taking hard water, deuterium D2O, in exchange of Nd, and they can see that the NH signal completely disappears. No coupling shown in proton NMR when the hydrogen is on a nitrogen. Chemical shift effects. Hydrogens on a carbon next to a nitrogen absorb at a lower field than alkane hydrogens. The NCH3 gives a sharp 3H singlet at 2.2 to 2.6. Carbon NMR. Carbons next to an amine nitrogen are slightly deshielded, about 20 parts per million downfield from where they would absorb if they were in an alkane. Mass spectrometry. Here's where that nitrogen rule finally comes into play. If your molar mass or your molecular weight in mass spectrometry is an odd number, that tells you have an odd number of nitrogens. Now, it won't tell you if you have 1, 3, or 5. All you know is it's an odd number of nitrogens. Alkyl amines cleave the carbon-carbon double bond nearest the nitrogen to yield an alkyl radical and a nitrogen-containing cation. So during the process of mass spectrometry, the molecule itself undergoes an alpha cleavage. We can see in this compound here that this is the alpha carbon, one away from the nitrogen, and it's between the alpha and the beta that this will break. We have the R group that was broken off at the beta position and further. That becomes a radical, but it's the nitrogen piece that has the plus charge, and it's the nitrogen piece only that gets detected in mass spectrometry. So you will see a peak with this molar mass. You will see a loss of this molar mass. Here's an example of a spectroscopy of N-ethyl propylamine. Let's take a look at its molar mass. The parent right here tells us 87, odd number, so therefore we have an odd number of nitrogens. This is our base peak over here. And we can see that in this reaction here, during the process of mass spectrometry bombarding with electrons, breaking up into its different ions and fragments, the alpha cleavage can give us 2 different fragment pieces because we have 2 different alpha R groups. So we would get a break here, and we would also get a break here, and that's why we have 2 different pieces being shown as our product as the products of our alpha cleavage.